The telegrapher's equations were the very first equations from electronics that were developed, invented for communication. This happened about 1.5 centuries ago, 150 years ago. The telegrapher's equations were developed by Oliver Heaviside after many companies experienced problems with very long distance electronic telegraph communications, like the first transoceanic cables were laid down in those years. Shortly after 1860, the first cables were laid down. And before these cables, there was electric telegraph was used at shorter distances. But at shorter distances, you didn't really have to know much about electrical engineering. There was just a key for the transmitter, an electromagnet for the receiver, and the battery that supplied everything. And this was a very simple equation to calculate these things. At long distances, other factors entered in the equations, namely the various parameters of the transoceanic cables. Since these equations are very important today, not just in communication, but in many fields of electronics, I am going to devote a whole lecture here just for telegrapher's equations in cables made with metal conductors and some kind of insulation in between. If we look at such a cable, such a transmission line, I may draw the transmission line as two wires. I may draw the transmission line as a coaxial cable. The transmission line certainly has an electronic equivalent circuit. There is a distributed inductance along the line. These wires do not have just inductivity, they also have resistance, and this resistance is losses, so we have a resistance distributed over along the line. We have a capacitance between the two wires of the line, or between one wire and the shield, or one wire and the seawater in a transoceanic cable. And we have also our insulation is not perfect, so this insulation also plays a role in the whole equation. So now these quantities are distributed inductance, distributed resistance, distributed capacitance, distributed conductance. They're all distributed components. I cannot replace the whole inductivity with just one inductor here, or with just one capacitor, or one resistor, or one losses in the capacitor where are conductance. This is also a resistor. Because as long as the line is short, this can be done. If the line is short, say if the length of the line is much shorter than the light traveled in one symbol time, so if symbols are much longer than the line length, then I could replace it with just one inductor, one capacitor, one resistor, one conductance here. But if the line is much longer than the single symbols I'm transmitting are long, and say in a telegraph cable over transoceanic distance we're just at the limits, so the limits, say the propagation delay is in the range of 100 milliseconds, and 100 milliseconds is also the length of the symbol in a telegraphic transmission, hand-keyed, hand-received telegraphic transmission. And so we already encountered this problem. And this problem was first encountered in the second half of the 19th century, and Oliver Heaviside dealt with this problem. So what can we do here with such a line? If we need to calculate things with distributed components, one possible solution is that I split the line in many short sections. Delta Z is very short, and I calculate the equations separately for each section. For instance, in this blue rectangle here, I describe the change of voltage from U1 to U2, and the change of current from I1 to I2, described with the internal components. I see that the voltage drop is only controlled by the inductance and by the resistance, and the current drop is only controlled by the capacitance and the conductance here. This is what Oliver Heaviside did. Now, chaining together many such sections in series means that the equivalent electric circuit will be very difficult to solve. If I think about a transoceanic cable, there will be perhaps 1,000 of such circuits. If I'm going to solve an electronic circuit using, for instance, a computer, I get a system of equations. And for every component I have here in my circuit, I get one equation. So 1,000 sections times 4 components per section, this gives us 4,000 components. And the shortest solution, the Gauss elimination, to solve the system of equations describing this circuit, is equal to the number of components to the third power, to the cubic power, divided by 3. So here I immediately get into billions of computations for just one single cable. Of course, this is even difficult to do today. It was even much more difficult to do it 150 years ago when Oliver Heaviside did this. So what we are going to do, we are going to try another way of solving this circuit. And the idea here is really to go into differential form. So to shrink every section to a differentially small section. And replace this finite difference, delta u, delta I, and delta z, replace them with derivatives. If I replace them with derivatives, I have now to keep care, because here I had finite differences here, and I have already had in the equation derivatives over time here. So current derivative over time and voltage derivative over time. So now what I'm going to get derivatives, partial derivatives. Now, if it's divided by delta z, the section length, this is going, when delta z limits to 0, this is going to limit to a partial derivative over z. So I'm going to have derivatives both over t here, and these are going to be replaced by partial derivatives, not conventional derivatives here, and I'm going to have derivatives over z. What is simplified is really here that when I'm calculating, say, the first equation, in the first equation, I1 plays a role. But in the limit where z goes to 0, I1 is simply I on this point, because there's very little difference. This delta I is very small if the length is very small, so I can replace it just with I1, with I of t and 0. And the same for the second equation, where I have this derivative du2 over time. Also, this derivative and u2 over time can simply be replaced by u of t and z, because z goes to 0. Rewriting the equations here, I have both partial derivatives over z, over the distance, and partial derivatives over the time. Today we shall also always have this coordinate z in the direction of the travel of our wave, in the forward direction. So z starts with 0 at the transmitter and ends with L, the line length, at the receiver. This is how we are going to know this thing. And time is going to be time. So I have partial derivatives over z, partial derivative over time. And now these finite difference equations, I transformed them into real partial differential equations. Two partial differential equations coupled because I and u play a role in both of the equations, and I have to solve. I have to use both to get a solution, or for just u, or for I. So these equations were first written down almost 150 years ago by Oliver Heaviside. What is also different in this equation? I don't use delta R, so the infinitesimal, the small inductance here, but I use the inductance over delta z. So this is the distributed inductance. This is actually Henry per meter length, not just Henry the inductance, but Henry per meter length. Here I have ohm per meter length, farads per meter length, and Siemens per meter length. And I'm going to denote this by L divided by small l, R divided by small l, C divided by small l, G divided by small l. These telegrapher's equations are sometimes not that easy to solve. There are some problems which are easy to solve, some problems which are less trivial to solve. So the first thing I'm going to do today, in the first hour, I'm going to talk about solutions in the time domain. In the time domain, if we go to time domain, in time domain, a relatively simple solution is if I have a lossless transmission line. Lossless transmission line means no resistance of the inductors and no conductance inside the capacitors. The equations simplify. The terms with R over L and G over L vanish here. And I can try to solve this equation, at least to have for a lossless time domain solution for the equation. This lossless time domain solution will already tell me a lot about the phenomena and the effects on transmission lines. So, solving these equations, how does it go? I derivate the first, if I want to solve the equations for U, I should eliminate I should eliminate the current. How do I eliminate the current? By derivating over Z the equation for U, and by derivating over time the equation for I. So if I take these new derivatives, these are just derivative versions of these equations. Okay, delta Z squared, partial Z squared is can always be computed. Partial t squared can also always be computed. But this order of derivation is first partial Z, then partial t, or first partial t, then partial Z. This is still a theoretical question for mathematicians. Can we change the sequence of differentiation? Yes, we can do it. We have physical signals that are very well behaved, like voltages and currents. There are no infinite values, no singularities here. So these functions, the order of derivation can be, the sequence of derivation can be changed here. If it can be changed, then I can insert the second equation, the bottom equation, in the top equation here. And in this way, I eliminate the variable I. So I get just a single equation for U. Second order partial differential equation, but with just one equation for one unknown. Here we had two equations for two unknowns. Now I have just one equation for one unknown. The minus sign cancels out. And now I have to look for a solution for this equation. How to actually solve this equation. And solving partial differential equations, many times it really helps if you can guess the solution. If you can guess the correct solution, here the trick is that I replace this function of two variables, this u of t and z. These are two separate variables that I have derivatives over one or over the other, with a function of a single variable x. And this variable x can be written as t plus minus z over v, where v is a constant. And if I look a little bit better to this expression here, this constant actually, the f of t is actually a function of time, seconds. Z has units of length, meters. So to convert meters into seconds, I have to divide by meters and multiply by seconds. So this constant v actually has units of velocity. This is physically very important because we will soon see what this velocity really means. So putting this solution, f of this t plus minus z over v in our equation, I have to calculate derivatives. So if I derivate twice over z, z is divided by v here, so I get 1 over v squared in front of the two derivation. This plus minus times plus minus twice changes to plus, so I have a plus sign here. And the derivative over t is simply the derivative sign here, the f prime twice, so two derivations of the function f of a single variable function f here, again of the same parameter. If I put these two things, this and this solution and this expression for the derivative over z and this expression for the derivative over t inside this equation, what I get that this 1 over v squared is simply equal L over L times C over L. 1 over v squared is this constant here. Or if I calculate v is now just 1 over square root of distributed inductance times distributed capacitance. Here. Very simple solution, and it has a physical meaning. If the line is a transversal electromagnetic line, so it has only transversal electric field, transversal magnetic field, then this V is equal to the speed of light in the media. Usually the media lines are usually insulated by a dielectric, so that I have to divide C0, the speed of light in free space, divided by the square root of the relative dielectric constant, relative permittivity here, relative dielectric constant down here. And so I see this velocity v has a physical meaning. It's not just a mathematical constant, it has a physical velocity. If I rewrite now the solution, I have to be a little bit careful. The mathematics allows both signs here with the same constant v, plus and minus. Of course, I get two different solutions for the plus sign and for the minus sign. And my final solution, since partial differential equations like this one here are linear equations, so with linear equations, any combinations of any number of valid solution is also a valid solution. So here I have two separate solutions with plus sign and minus sign, and any linear combination of these two solutions will give me a good solution, will solve actually this equation here, up here. So, how do I call them? The one that has the minus sign, I call it forward wave. We shall see later that this wave here, function UF, voltage forward, should have a minus here, so that if time advances, z should also advance to keep the same value inside here. While the reflected wave has here the plus sign. So reflected wave, if I increase the time, z should decrease to keep the value under the function constant. So this already tells a lot about our solutions, but otherwise UR and UF are arbitrary functions of a single variable, and the single variable is written inside the parentheses. So this UR is completely independent of UF, and they are arbitrary functions, but the only limitations really imposed by our equations is that, well, these functions have derivatives. That's of course a must. If you want to write down differential equations, you need the derivatives, and these functions must be of just a single variable x here. So this is about the solution for the voltage. Let's see what happens with the current. I can rewrite just one of the equations, like the top equations here, the top equation I have on the previous page here. I can rewrite this top equation for the current and putting for U and I what I have available. U and I what I have available. Here is this parenthesis should be on top here, or this partial sign in front of this. So this parenthesis should be in the numerator of this fraction here. This is a mistake here. Of the function I in the second row. I already have written this, so I is written now with the prime here. I is missing in the top equation. I is missing. I have it here, and u prime is also a derivative of this one, and I get plus minus 1 over v because of this plus minus, and I have a single derivative, not a second derivative like in the. And I get now the ratio between u prime and y prime. If I turn around this equation, because of this minus sign here, it becomes minus plus v times L over L. So this is minus plus square root of L over C, so distributed inductance divided by distributed capacitance. And we also call this square root the characteristic resistance of our line. Now, if the derivatives are in this fixed ratio, except for an additive constant, also the same functions u and I should be, the ratio should be identical. So if there are no constant terms here, no DC component, then the ratio of the derivatives is equally, with no derivative, with no DC component, is equal to the ratio of u over I. So if I rewrite this equation a little bit less confused, the characteristic resistance is this square root of specific inductance divided by distributed inductance divided by distributed capacitance. Or for the forward wave, I have the plus sign, because the plus sign was this minus here. This is forward voltage divided by forward current, or minus reflected voltage divided by reflected current. And these two solutions are again totally UF and UR are totally independent, IF and IR are totally independent. Rewriting the equation for the current wave, in place of putting currents here, I can simply put voltages divided by RK, the characteristic resistance here. So I can also write down the current wave. It's very similar to the voltage wave. The voltage wave in both directions is here, the voltage waves. But the current waves has this minus sign here with UR. So because of this minus sign here, if I look here at my equivalent circuit, here I have UF and IF drawn in the conventional direction, but UR and minus 1R is actually flowing backwards, because this is the reflected wave from the load. And it can be shown that I can mathematically correctly describe my line by stating V and stating RK. So if I state the velocity and the characteristic resistance, I completely described my line. In fact, these are two variables derived out of these two variables, L over C and C over C here. So now I have a complete description here of my transmission line. Now, something that makes sense is to, maybe we should look first at the next. The next, this one we shall look at the next graphs later on. So now let's look at the yet another definition. We have lots of definitions here, but these are actually quantities that are being used in practice. So we have to learn what are they. So from the fundamentals of electrical engineering, we know about the Ohm law. We know that the current through the resistor is the voltage, if this is a lossless line, divided by the resistance, the load resistance. And this is very simple relationship, the Ohm's law, in the world where there are no distributed components like here. But with distributed components, it makes sense to define these resistors in a different way. It makes sense to define this resistor as the reflection coefficient, the ratio between reflected wave voltage and forward wave voltage. The reflection coefficient is always specified for voltage. Of course, we would get the opposite sign using currents here. Voltage, or if these are fields, electric field, or this is acoustics, it's velocity and pressure of the particles. But actually the reflection coefficient is a quantity that's defined for many different waves, not just wave on the wire transmission line as here. So it's a much broader expression than resistance of the resistor. And therefore it makes sense to calculate the reflection coefficient from the resistor, or vice versa, we can calculate the resistor from the reflection coefficient. Here are the equations. What do I do with the equations? The voltage is simply the sum of both voltages. The current is the sum of both currents, but expressed with voltages, I have the minus sign with UR. And I can translate this into an equation that has UF minus UR here. So I can simply sum this equation to have these equations to have the forward wave, and subtract these equations to have the reflected wave here. The ratio of the two U reflected divided by U forward is our reflection coefficient. And if I look, this can be very simply expressed with the resistance, provided that Rk is known, provided that this information about our transmission line, or the free space impedance of space if this is electric and magnetic field, or the acoustic impedance of the media if this is velocity and pressure of the sound particles for acoustics. Of course, I have relationship in both directions. This gamma is a very nice quantity because it doesn't raise to infinity. Even if our resistor goes to infinity, gamma, still for real loads, for passive loads that actually absorb power, this R is always with R greater than 0 but less than infinity. This is also finite. So gamma is also finite, and gamma can span between -1 and +1. For in the time domain, as we did it here with resistors, gamma is a real number between -1 and +1. We shall see later that for in the frequency domain, gamma may also be a complex number. So how do we measure gamma? Well, even the measurement, if we cannot measure something, then we are in troubles. But gamma is actually easy to measure. Usually to measure the resistance, like here, I need a perfect voltmeter to measure the voltage with an infinite internal resistance. And I need an ideal ammeter to measure the current with 0 internal resistance. Such instruments in reality do not exist. Even a source here with 0 internal resistance does not exist. So we are really in troubles with the standard theory of electrical engineering. We are in troubles because the Ohm's law, the individual quantities are already difficult to measure. In the case of the reflection coefficient, we can make the following trick. We build a reflectometer bridge. This is this circuit inside here. The reflectometer bridge is a little bit different from other bridges that from the Wheatstone bridge that we typically learn at electrical engineering, in the courses of the electrical engineering. The reflectometer bridge, we usually use it unbalanced. So we actually measure this difference from V3 to V2. And this is actually our measured quantity. But the very trick is that here we have a non-ideal source. We have a battery, a generator, that has a finite internal resistance. This resistance should be equal to Rk. We also have a non-ideal voltmeter that can be built in practice. So this non-ideal source can be built in practice. This is a practical solution. And this non-ideal voltmeter here is also a practical solution because we can build a voltmeter that has a finite internal resistance equal to Rk. So these two are no longer theoretical, infinite impedance or 0 impedance like in standard electrical engineering. These are really available components. Then we need another 3 resistors equal to Rk of our line. And we have an unknown load that's not part of the reflectometer bridge itself. So now what we can do? We can try to solve this circuit in this green rectangle here that has 1, 2, 3, 4 nodes. We ground one node so that we can put on nodes 1, 2, and 3, we can write here the node equations for the potentials. Trying to solve these equations, how do we solve them? We start with the simplest equation. From the simplest equation, we pull out V1 to put V1 in the first and third equation. The third equation is the most complicated because it's just R here, not RK. So we try to solve the first equation first. We get out V3 from this first equation, and finally we put V3 into the final equation. V3 was a thought quantity because we need V3 to calculate the voltage flow across the voltmeter, and from the final equation, the most complicated, we calculate also V2. If I now calculate the voltage on the voltmeter is V3 minus V2, potential of V3 minus potential of V2, I get this expression that looks complicated, but this can be abbreviated in a very simple form. The voltage over the voltmeter is just the voltage of the generator divided by 8. The voltage of the generator divided by 8, and here I have gamma. R minus RK, R plus RK, this is actually the reflection coefficient. So the reflection coefficient can be very simply calculated from this is the generator voltage, the voltage shown by the voltmeter, times 8 multiplied by 8. This is the factor of our circuit here. So I have the Reflectometer Bridge is a very nice device here that can solve many different problems. Here all these cases here, actually the reflection coefficient and the Reflectometer Bridge were operating at DC. So DC comes a little bit boring. We should look at the transient, what happens when we turn on the switch. And here we look at the simplest problem here. So we close the switch at t0, and we look what kind of transient happens on this line here. The line is not terminated, it's terminated into an open circuit here. So when I turn on the switch, a forward wave will start propagating along the line. The forward wave that's actually equal to the generator voltage here. The forward wave. Of course, as long as large t did not elapse yet, large t is the propagation time over this line, nothing happens on the output. On the output we have no voltage here. But as soon as this forward wave arrives to the end of the line, now it is reflected. It is reflected from an open circuit. An open circuit with a load resistance of infinity and the gamma of +1. Here, this open circuit has a gamma of +1, so reflects the reflected wave with the same polarity as the forward wave. And this reflected wave now goes back towards the generator. In all this time, I have twice the generator voltage on this open circuit. Not generator voltage, but twice the generator voltage. I have an overshoot actually here. And as the reflected voltage comes to the generator has a resistance of 0, so gamma -1, so it's reflected in the opposite phase. In the opposite polarity. In the opposite polarity, it subtracts for the previous forward wave, and now the forward wave vanishes because it's original forward wave, and this reflected wave, is reflected a second time from the generator, so it vanishes. And this front now goes with the +V in the forward z direction, but after him there is only the reflected wave left. We are here still at twice the voltage here at this point. As soon as after 3t this forward wave, vanishing forward wave, came to the end of the line, to the open circuit. Since there is no longer any forward line, also the reflected line vanishes. And here we drop down to 0 here. 0. And this remaining energy in the line of the reflected wave is now slowly being sent back to the generator. The generator still receives here energy from the line. Here the voltage is 0, and after 4t we come to this point here. We come to our initial point, no waves in the line, no energy in the line, and then the cycle can repeat. So this effect is called line ringing. It's a very nasty effect. It is always a problem in computers and computer communications, and we shall see more details about it later on. this line ringing has also a lumped circuit equivalent. A lumped circuit built with just a single inductor and a single capacitor. Here we observe the same kind of ringing, but while this ringing of on the line was a square wave, this ringing on the lumped component circuit is a sinusoidal wave. Still, the sinusoid goes from 0 to twice the generated voltage, back to 0, back to twice the generated voltage, and so on. It is very similar, but the shape is different because this circuit is made from just two components. Here I have distributed components that can actually transfer a very wide frequency range of signals, and higher harmonics will transfer. If harmonics are present, then in place the sine wave is replaced by the square wave here. Now, in computers, it is very important in computer communications to get rid of this ringing. We are always discussing this thing in time domain. Frequency domain is left for the next hour. So how can we suppress the ringing? To use some kind of source termination, so we add the resistance, internal resistance to the generator, or we put some load resistor on the line end here. And what happens now? Let's see the first case. We have we change the internal resistance of the generator, and we leave an open circuit on the end of the line. The end of the line is infinity. RL is infinity, open circuit. What happens if I change this RG? If I change this RG, the simplest thing here is that the voltage at the end of the line simply jumps to the generator voltage. In reality, here what the generator is doing when we have RK here, the generator is putting here a forward wave that has just 1/2 of the generator voltage. But when it is reflected, it jumps to full UG. So it jumps to full UG here. If I go down here, jumps to full UG and stays there. Because the reflected wave, when it reaches the generator, if generator is RK, then its gamma, its reflection coefficient, is equal to 0. Nothing happens anymore. So this is a stable picture, and this is what we are looking for. Stable voltage. If we put a resistor that's too small, then the reflection coefficient will be negative. Negative, just like in our previous case here, when we the polarity of the reflected wave flipped here and destroyed the forward wave here. And in this case, if the resistor is smaller, I have a similar ringing, but this ringing decays, the amplitude of this ringing decays with time. So this is a decayed ringing. But it's still an overshoot. I can still get pretty larger voltage than the generator voltage if the R generator is smaller than RK. On the other hand, if the generator internal resistance is higher than RK, then I also have a reflection, but now gamma is positive here. Because it's positive, the reflected wave, twice reflected wave, adds to the forward wave with the polarity, and our ringing makes no overshoot. It's just ringing towards its stable, steady state conditions at the end. Of course, this solution is the best. R generator is equal to RK. We can also try to do things on the other end. So we leave R generator to 0, and we select the load resistance. Of course, if load is equal to the characteristic resistance here, then we have no reflection at all. We have this ideal case with except for the delay t, the output is equal to our input, except it is delayed, and we cannot get rid of this delay. Of course, we cannot get it because this is light speed in between here. If this resistor is too large, we have overshoot. R load is too large. If we have the resistor is too small, then we have this slow approach to the final value. So with load source or load termination, we can improve things. Of course, the best solution is to use both source and load termination. Why both? Because with both, we have to think about component tolerances, that are tolerances of the resistors. There are tolerances of the characteristic resistance of the line. So this is also may have tolerances. And in order to suppress better, it's better to have both this equal to RK and this equal to RK. But then we only get half the voltage here of the generator. UG half we only get here. So this is not particularly attractive to have this solution. But it should be done when the line is particularly demanding, where the line is particularly sensitive to the termination. So let's see how we do with this with digital circuits. The first on the top example here is a typical computer bus in, say, a personal computer. We have a microprocessor and we have a memory. CMOS circuits nowadays have an output resistance that's very, very, very small. That's much smaller than RK. And on the other hand, the receiving side should receive the full voltage, because CMOS circuits work with fixed switching threshold, so we cannot change the voltage here. So we prefer to leave the input here an open circuit, and a CMOS input, it's almost an open circuit, a few picofarads capacitance and nothing else. And we put the termination just on the transmitting side, on a unidirectional bus, like the address bus inside the microcomputer. This termination takes the form of resistors. These resistors are frequently soldered on the motherboard of the computer. On many occasions, there are four resistors in just one package with 8 pins and SMD components. So to have a 4-wire bus terminated with just a single SMD component that contains 4 resistors. On the other hand, if we have two bidirectional bus, like the data bus, where the microprocessor may write data to the memory, but the memory the microprocessor may also read data from the memory. So this one may transmit and this one may transmit. We put series resistors on both bus ends. So during memory write, this one is working, and during memory read, this one has a function. We didn't change any logic levels here, so this is okay. And the other thing that's okay here, that's very attractive here, is that in the steady state, when this one is not switching, or this one is not switching, or this one is not switching, there is no power drain in this circuit. So this is a very low power circuit, and this is important today in computers because of the vast amounts of heat that are generated in computers. On the other hand, if we don't mind about the power drain, then we use emitter coupled logic. Emitter coupled logic, we use termination at the receiving side. Here we use termination always on the transmitting side. Here we use termination on the receiving side. And the output of an ECL circuit is, its output impedance is very, very small. Very much smaller than RK. This line may have about 100 ohm characteristic impedance. And on the receiving side, we put a termination resistor. This termination resistors for very high frequency may be embedded inside the chip itself. So it may not be an external resistor. An external resistor may be used perhaps to 1 gigahertz, but above 1 gigahertz, you have to use an internal resistor. The standard supply voltage is minus 5 volts for ECL logic, and the termination voltage is minus 2 volts, and there is usually a special power supply for this minus 2 volts. So this is about computer buses. Computer buses are relatively short distances, and people usually don't know what is inside their personal computer. But ECL logic is not that popular. There are even other logics that are being used. I just showed here the most popular ones used in computer. Another thing is external communication. Say, wire cables connecting one computer to another computer. And here you can look what kind of solutions were used here. So computers started with no termination at all. Computers started with the RS-232 COM port, communication port, operating guaranteed just up to 19.2 kilobits per second over a range of just 18 meters. This was just enough to connect the computer to the printer or something like that. The characteristic resistance of this line was around 100 ohm, but it actually was not used even not used correctly. Usually one line was grounded, so this was not a symmetrical line. The blue line was grounded, just the red line was carrying the signal, and the output resistance of the transmitter was chosen much higher to the characteristic resistance of the line. So therefore, if I go to these solutions, we have chosen with RS232, we are using this solution here. High resistance of the transmitter. In addition to this, also the slew rate of this transmitter was limited with some additional capacitors. Maybe mainly to avoid radio interference, because of in those times engineers were very concerned about radio interference caused the computer combinations caused to radio reception. This was of course not a good solution. Very low rate at very rather modest range here. A little bit better solution was the universal serial bus. Operating initially USB 1.1 was 1.5 megabits and 12 megabits. Let's look at the 12 megabit solution. USB is defined to have a twisted pair with a characteristic resistance of 90 ohms. It's operating in a symmetrical regime, so the transmitter is completely symmetrical and all both inputs of the transmitter have a 45, one half of 90 ohms, 40 half ohm output resistance. So I match, now here I had a high impedance source, here I have a matched source, a matched generator to this line, but I do nothing on the receiving side. On the receiving side I leave the input resistance as high as possible. This of course can work at a limited speed, 12 megabits per second, over a limited range, 3 meters range. So it's not a particularly good range because there's no termination on the receiving side, and tolerances of the transmission line, this is plus minus 15%. Tolerances of the resistors do their problems, add and add the ringing also on this line, because components are not perfect. So USB was invented by computer hackers, and that's the reason why it's not a particularly good standard. A much better standard is the Ethernet. Ethernet was invented by engineers. Engineers that knew a lot about communications, knew a lot about radio interference, and they tried to install all this in their circuit. So 100 megabit per second Ethernet. Okay, it uses 3-level coding, so the data rate is actually a little bit lower than 100 megabit. Uses a characteristic impedance, a twisted pair of 100 ohms. Over 100 meters range, the typical value is 150 meters here. And this transmission line is terminated at both ends. It's terminated at the transmitter with 100 ohm, symmetrical, so this is 50 ohm in series of the true output and the complementary output of the transmitter, and it's 100 ohm between the differential inputs of the receiver. Ethernet is certainly much better because engineers designed it, not computer hackers. That's the difference. And finally, how to go up to 1 gigabit per second if the bandwidth of this copper line is still quite limited because of losses, both the copper losses and the electric losses. But still we have a 100 ohm line, 5-level coding. But in this way we can only reach 200 megabits per second per twisted pair. Over 4 these twisted pairs of the standard UTP cable is this 1 gigabit. 200 megabits per 4 twisted pair is 100 gigabit. But there's yet another trick in the Ethernet link. The other trick is using reflectometer bridges on both ends of the link. So I connect my transmitter and my receiver on the same reflectometer bridge. On the other end of the link, I do the same. I connect a receiver and transmitter on the reflectometer bridge. And this transmission, if these reflectometer bridges are made perfect, can have very little crosstalk between the communication in this direction and the communication back. So the Ethernet 1 gigabit is bidirectional, using bidirectional transmission on the same transmitted pair and handling this transmission with reflectometer bridges. Because the reflectometer bridge has exactly this property. The reflectometer bridge is able to generate here the forward wave and have here only the reflected wave. This is the trick in the reflectometer bridges. And if you look at this circuit a little bit strange on this lecture, you should know that at home, if your computer has a 1 gigabit Ethernet port, it has at least 4 reflectometer bridges built in. So this is now a standard piece of equipment built in computers. This is enough for this hour. So to make it short, next hour we are going to talk about the frequency domain, where several other interesting things happen.